So for uniform distribution, uniform distribution is a very important distributions in Monte Carlo simulation because number one, most of the number generation, whether for uh, any other uh, statistical distribution like normal distributions or um, discrete distribution like binomial or Poisson, we can use uniform random distribution to generate that. And in the statistic class specifically, they should teach you how to generate different kind of statistical distribution using uniform random. And the property of uniform random distributions, they have the mean is equal to A plus 1. Number one, they must be in a specific range. So distribution of value between A and B, the function, the probability function can be given like 1 multiplied by B minus A, where B and A are the boundary of that values, okay? And in this case, X, of course, must be less than A, and X must be also less than B. It must be greater than A and B, or it will be between A and B, because it must be in the middle between A and B, okay? Any value, the value distribution will be between A and B. So they can be given by this probability function. And the second probability property of uniform distribution is A and B. That means the lower boundary and the upper boundary, when we add them together and divide them by 2, they will give us the mean or the average. And the variance is equal to B minus A to power 2 divided by 12. So you learn that in any statistical distributions, when somebody asks you about statistical distribution, any kind of distribution, always think about what is the parameters for that distribution. We know that for binomial distributions, we have N, which is the number of trials, and P, which is the number of success. And the same thing also for Poisson distribution, we have a single parameter, which is lambda. Lambda is the rate of that event, okay? And in case of normal distributions, we have the mean and variance, okay? And in case of uniform distribution, we have 2 parameters, which are the interval, okay, A and B, because most value will be there. And we will begin, because this distribution is really very important, okay? We use it to generate random number. A random number is the essence of Monte Carlo simulation, okay? So we say that whenever we need to simulate anything using Monte Carlo simulation, we have to think about how to generate random number. And after that, we will just use for loop or any loop to generate many numbers. And as we will see in next example, okay? But generation of random number is very important. There is no any Monte Carlo simulation without generating random number. And in any language, not just in MATLAB, but in all language, they employed or they implement different kind of function that can do the same kind of function. And in case of MATLAB, to generate discrete variable or random number, we can use rand_i. which is random integer. And when we use this function and we put 6 as argument, that means it will generate a random number between 1 to 6. So every time you run this, you will get a different value, like rand for random and I for integers. And if you put 5, you will get 5, you get 4. When you run it for the second time, you will get 3 or any random number. So every time you run it, you will get different value, and that value will be between 1 to 5. So that means you are simulating or you are generating random number in certain interval. An interval here is between 1 and 5. Okay. And so every time you run this, you will get random number. Okay. And that random number will be between 1 to 5. So if you need to generate number between A and B, and say A is equal to 5 and B equal to 10, then you need to put them in this form. Okay, you have to put them like a list. You put rand I and then 5, 6. This will generate a number between 5 and 10. Okay, so anytime again you run, you will get a random number between these two values. Okay, and you know that depends on your experiment, because here we are dealing with Monte Carlo simulation, and you may find yourself in different situations that you need to create different kind of different kind of simulation. So you need to, okay, so when we come to simulate the dice, and we know the dice has 6 faces, then we will use the argument here will be 6, because we need number to be generated from 1 to 6, right? You may find yourself in different scenario using different discrete number. So all you need to use rand I, and then you can put the interval or the lower limit and upper limit, and that will generate a number between these values every time. Okay, so this specifically, this is really very important. Okay, and there is a different ways here to generate this random number, and we focus in generating random number because that will most of the simulation we are using this kind of thing. So now we need to generate a random uniform variable. We talk about how to generate a variable. That means it takes multiple value. A single value, it's just a single value, but when we talk about variable, a variable that it can take variable values. It can take values. Okay, so now we need to generate a because already we know that so every time we use randi, we will get a value. Okay, so now we need to simulate how to generate a variable. Okay, a random uniform variable using randi. Okay, and also this it is generating of a random variable, but also it can be considered as Monte Carlo as well. But let me to create to open here a script file. Let me to save this file to give it any name. So like let's call it like uniform render uniform one is fine. To just to show you how we can how we can generate that. And already we know that randi, okay, we 6 or 5, it will generate a random. Okay, so we're gonna write this, type this here in the script file, and let it give us R variable, okay, to be R. Okay, so because here we are generating a, now we generate this like just one time, okay, but we need to repeat this different time. Okay, say about n, this would be the number of trial, okay, and let it be like 100 times, okay, and then we need to create one-dimensional array, and let us give it like s, okay, or yeah, it's small s equal to 0, 1, n. Okay, so this means that we are creating, actually we are creating a one-dimension array, but 0. This is just to allocate area in the memory. And let me show you how this function, how zeros, how 0 function can do something. Okay, so 0, 1, 5, it will create one-dimension array, but all elements are 0. Okay, let's do this. Okay, if you see here, we create one-dimensional array, and the element are zeros. And the idea is just to reserve area is the memory, or we create one-dimensional array empty, and later on we will fill it with with some values. And here specifically, we need to fill it with the random value that we generate in every iteration. Okay, and so the next step, because we need to generate this, and already we know that every time we run we generate a discrete number from 1 to 5, and we need to repeat this different time. You can use for loop all the time. So I is equal to 1 to n. Okay, just to make it simple. Okay, so like n, and if you see here, whenever you see any red line, that means you are missing something. And the idea, if you hover on the top of that red line, it will tell you what you should, it will remind you something that you shouldn't forget. And here it reminds me to add n, and this is what I'm going to do. Okay, because if you have for loop, then you need to end it with end, because every statement in the middle will be repeated, will be iterated many times. Okay, and here iteration from 1 to n, or 1 to 100. Okay, so now we generate, but still we need to store, because we need to store the volume generated by randi 5. Okay, so already we created s here. So instead of r, we can type s, because we reserved one-dimension array for this purpose here, to store the random values that generated by randi. And because this is a an array, then we have to use the 1i, because this is index. Here we have one row and we have n column. And as the same thing here, like in every iteration, it moves from element to element, and that the value of that element is 0, but will be updated by the random values that generated in that experiment. And we call this, we are repeating the experiment, okay? Before we show you how to do single experiment, but by using for loop, you are simulating repeating experiment or trial n time. So any time, so like when I is equal to 1, you will generate a random number. We don't know what that random, but that random number will be stored in 1, 1. And again, this will be incremented to from 1 to 2. Again, this will be executed and generated random number. A random number will be stored in this array in 1, 2, and so on until it reach to 1n. Okay. So now this will be repeated until the end, and at the end we will have s. Okay. So from this, the idea is just we want to know how the idea we need to generate a uniform random number, okay? And the best way to know whether that random number is, is uniform, we can use histogram, and S, okay? That will tell us if, again, just always try to make everything logic. Don't forget anything. I is equal, you can check. And anyway, also we need always very good practice to add clear, to clear any variable in your workspace. And also you can use CLC to delete any any kind of text here, just to make anything very clear. So let me run this, and if there is any error, like this here, because if you put comma, that red it will remove, because otherwise it will print it. It's not like error, but it remind you. It will print that. Okay, so let me run this and see how it's gonna turn out. We get this. If you notice here, we get, because it is from 1 to 5. So like in this 100 trial or experiment, we generated this number and number from 1 to 5. And because the generated number are very small, 100, so we didn't get really uniform, 100% uniform values. We expect that all value from 1 to 5 to be uniform, that they have the same level. And this is because it's a stochastic process. When your number of samples or number of threads is very small, don't expect to get that uniform distribution. So let us increase this to 1,000, okay? And all we need to increase the number of trials, and everything will be substituted here. And then let us run this again. And if you see here, we come to some extent very close to uniform, but it is not uniform, okay? So let's close this and put another 0 and see how that will be improved. So if you see here now, it is improved, right, a little bit, but it's still the value are not distributed. And the idea of uniform random variable, all values from 1 to 6, they have the same chance to be generated. So they have the same probability. So why they are uniform, and why we are using them to generate the numbers for other statistical distribution. So let's just increase it as much as you want, and to see how that will be reflected on the histogram. Of course, it's going to take time, because when you increase the number of trials, that is going to repeat this loop many times. But the result is, when you repeat this many times, you will get real uniform distribution, and no one can say that this distribution is not uniform. Okay. So the takeout from this, if you need to use Monte Carlo simulation, you can increase your number of trials as long as your computation resource allow you to do that. Okay. And if you see here how this really, at the end, you get this kind of uniform distributions when you increase the number of trials. So let's do something else, because this is a simulation, and already we know that the uniform distribution, discrete uniform distribution, already we know the variant and the mean. Okay, we know the mean is equal to that, like in this case, because here between 1 and 5, then the theoretical mean is equal to 1 plus 5 divided by 2. Okay, divided by 2. Let's show you the maybe I'm wrong. So this is A, the mean is equal to A plus B divided by 2, and the variance is equal to B minus A to power 2 divided by 12. Okay, so this is the theoretical or the actual whenever between two rows. So let's so this is the mean is 3, and the variance is equal to 5 minus A minus 1, because the range is between 1 and 5 raised to power of 2, and then divide by 12. Okay, so if you see here, this is the mean and the standard deviation. So let's calculate mean and standard deviation from here, and we can just type mean S, capital S, and var, this is another function for, let's print this and see how they will get okay. So yeah, if you see, it's very close, right? It's very close. This 2.9 and this 1.9 for the variance. Okay, and so on. So every time you increase it, will become more accurate, and we will in the future, when we simulate a different situation, we will come to this. We call this some kind of convergence of values, and it helps us to evaluate our simulation system. But we don't need to spend too much time on this, because we're going to move to different kind of simulation. But the idea is to understand how you can do Monte Carlo simulations by generating the numbers, and then you can repeat that. Most of the time you can use for loop, and you can use this in all programming language. Okay, you are using the same principle. So now assume that instead of 1 from 5, we need to simulate between 5 and say 10. Okay. So now we expect that the values generated will be between 5 and 10. That means, and they must be uniformly distributed as well. Okay, let's run this. So here, the reason why, because they must be in a list form like this array. Okay, let's do this. It might take some time, otherwise maybe we didn't close. Yeah, we didn't close this before, so you need to close it and simulate. Okay, see how. Yeah, so now if you see, it is between 5 and 10. Okay, and the generated number are even. That means all of them, they have the same counts to be generated. We don't have, they are uniform. Okay. So we will use this property of uniform discrete variables in other Monte Carlo simulation. Okay, so you need to just go through the codes, and the code is right here, and you will understand. Okay, so now we will come to simulation, very basic simulation. Okay, like in any Monte Carlo simulations, they will begin with flipping a coin, because this is the first simulation, and this itself lead to the invention of Monte Carlo simulation. So why in any Monte Carlo class, they will begin with how to simulate flipping a coin. And we know that when you flip a coin, and this is very simple experiment, and all you need just fair coin, and you flip it many times, and every time you record the outcome, is it tail or head? Tail or head, and you flip it, you keep flipping it. You can repeat this experiment as many as you want, 200 times, and at the end you count the number of head, and then you count the number of tail, and then you can find the out like how many you can compute the probability, or the number of. So in a typical binomial distribution experiment, we expect success and failure. Okay, whenever we have any experiment of two outcomes, success and failure, always we think about flipping a coin. Okay, because we say that it must follow a statistical distribution, and a statistical distribution of flipping a coin is binomial distributions. And already we know that the parameters are the number of trials and the probability of success. And if you think about a coin, because it has only two outcomes, then the probability of success is equal to 0.5. Why? Because we have two outcomes and they are fair, then the probability is equal to 1 divided by 2 events. Okay, because the total number of events is 2, and the probability, the total probability is 1 even. Okay, so we begin with this, and let's go back before we to how to simulate this. Let me to this again. Let me delete this because already we have, or let me to save it as well. Uniform one, this to go to uniform 2. And this, what this coin, right? Coin, we can call it like coin flipping. That's 2, okay. So now I create also another function, but for here specifically, we're going to use rand function, okay? So when we click this, it will give us a continuous number between 0 to 1. So every time we run this, we get a random number, uniform, continuous random number between 0 and 1, okay? But let us see, always, every time it will give us the same thing, okay? But we need to use this, and the probability of getting, because actually every time we run this rand, it will generate a random number between 0 to 1. Then the number that we get, if we keep repeating this experiment like many times, the number of time in which we can get a value less than 0.5 will be approximately equal to the number of values more than 0.05, okay? So the probability will be even, okay? So the probability of getting any random value more than 0.5, it will be, the probability will be 0.5, okay? And at the same thing, also the probability of getting value less than 0.5 will be 0.5. So we can use this property to simulate tossing coin, okay? There are different ways to simulate coin, but this is one of them, okay? So let's do rand. If we are random variable equal rand, so every time it will generate a random number between 0 and 1. But we need to benefit from these properties, okay? So we want to say that if a random value greater than 0.05, okay? And again, if you see here, if, always we can close it with end, okay? So we get that red line off. So if we random value, then if R, we need to print, okay? And this time I think we do F print head, okay? So if any step that you didn't understand it, please let me know, okay? So when the random value that generated by rand is greater than 0.5, then we consider this as head. Else, the will be tail, okay? Because we know that when we simulate flipping a coin, we have two outcomes, either head or tail. So this is a single experiment. Let us generate this, but before that, always better to clear any thing. And okay, so let's run this. So clear random, if random value if is R greater than, then print F8, else print end, okay? CH, okay? So anytime we run this, So let's clear this, okay, because this it will clear the output too. So we need capital. So every time we run this, we will get tail, head, 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 tail, tail, head, head, tail, so on. So this is a random outcome, okay? So this for a single experiment, okay? Because we have a single experiment, we generate a random, and then we use the property of random value because it is from a decimal from 0 to 1. So, and we know that the probability of getting more than 0.05 is equal to the probability of getting less than 0.05, and each of them will be 0.5 or 1 divided by 2. It just like, so we benefit from this to whenever R is equal to 0.5, that will be success if you consider getting head as success, else it will be 10, okay? So like this, we can generate, okay? But this is a single experiment. We can, again, we can create for loop in, the actual is 100. And then we can create for loop for 1 equal 1 to n, okay? And here we need to close this with end, and it will be more organized if we okay, it will be more organized if we put them like this, because everything here will be repeated, okay, like every time it will be repeated. Okay, so let's run this because here they will, okay, let's just make it only 10 times to see the output, okay, how it looks like. So we'll get this. If you see head, they can be all head. Okay, let me see what is the problem here. Yeah, random supposed to be here. So because every time we generate this random, okay, so it must be inside the loop. Otherwise, we will get a single volume. So let's clear this. Okay. Now when we run it, if you see, we get head, head, tail, head, head, tail, and so on. So when we increase the number of experiment, we can create, we will find now to the 100, we will find head, head, tail, tail, and head, and so on. Okay. So like this, we simulate a flipping a coin, and in every trial or experiment, you are getting an output, and you cannot predict that output, but it can be, or it can be either head or tail. And if you see here, you will find head, head, tail, 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 head, tail, and so on. And this is in random way, okay? In random way. So this in random way. We can do instead of this. So are you following me? Do you have any question? So everything is clear?
Yes.
Okay, if any point not clear, just let me know, okay? And so now here we are simulating flipping the coin, and we get in any outcome, we get this. But we need to compute the probability, okay? We need to compute the probability to see how is it true or not, because we know that the probability of getting, even if we repeat the trial different times, at the end, we should get 0.5 probability of success, right? Because it is fair coin. So let us do something. By store, we create one-dimensional array, zeros, first let's to make it 0, zeros, 1, n. Okay, so this is the we create a single dimension array with 1 and n elements inside. Okay, because we need to store the values here, because if it is success, so whenever if it is greater than 0.5, that means hit, then we will consider as success. So we need to store this in S1I, because this will change, okay, equal 1. Okay, so we need, whenever there is a success, we're gonna add 1, okay? Otherwise, if it's not success, failure, then we need to store that as to be 0. Simple like this, okay? So now we'll be able to compute the mean and variance, because we are getting a vector that for each value, if it is h, if it is h, it will be success, then they will add 1. If it is failure like t, it will be 0. So when we sum them together, then we can compute the number of event, or the number of success. Okay, the number of success, and after that we can get the probability. Okay, so now let's do this. Now we have a vector that either include S or include 0 or 1. 1 for success, 0 for failure. Okay, so we can, if we sum it, we know the number of success. Okay, let's sum this and run it. So that means we have 75 success. And it is something expected. Why? Because we have n trial, and we expected the theoretical, the ideal, supposed to be 50. But because this were random generation and the number of samples is small, but still we get the number of success very close to the theoretical number of success. Because if we flip a coin 100 times, then we expect, our expectation is to get 50 head and 50 tail. But because this here we are simulating this process, we get 57. Actually, 57 is not bad, okay, because this simulation. And when we increase, every time we increase, we assume that we expect to get more close value to the real value. Okay, so let's here we expect like to find 500 and 500, right? 500 success and 500 failure. So when we run it, you see we get 499. I think the difference is only 1. Okay, you may not get exact number actually, and we are not looking for, because it's stochastic process. Okay, it's not like something that you will get the output exactly. Okay, it is random process. But this, it tells you that when you simulate, when you use this matrix simulation, Monte Carlo simulation, when you increase the number of experiment, you will get more accurate value. Okay. And of course, from here, we'll know that the probability is almost 0.5. And computing probability is very easy. So all we need to sum of divided by the total. Okay, this is a probability, right? Because the total number of trial and the number of success divided by number of trial, and we'll see this is equal to 0.5 probability. Okay, so this is how to simulate how to simulate flipping dice. And this is the key, because if you understand this, then you will be able to to simulate, to make different kind of simulation. And we have many situations in our life, in our work, we can use Monte Carlo simulation. They might be in discrete scale. Then they might be in continuous scale. But if it is in discrete scale, you can use this process to understand how to simulate that processes. And next time we will simulate second example as well, how to simulate tossing two dices, and also this one of the problems that if you take in any Monte Carlo simulation, also because they are very simple, and at the same time they can generalize this to real problem in our life. Okay, and we see that. So next time we will discuss simulating tossing of two dice, and after that also we're going to expand this to real life problem, and so on. Okay, so this is how to just still we are in the first step of Monte Carlo simulation, but this should give you idea about how to use Monte Carlo simulation to simulate any any situations. It depends on probability statistical distribution, number generation, repeating of experiment. Okay, they depend on this. So do you have any question? So everything is clear, right?
Yes.
All right, if you have any question, feel free to ask. And I may give you assignment. It is about what this just few code that I gave you in MATLAB. Just you repeat what already I gave you here, and that is it. Okay, the idea to understand how to use this code and how to generate numbers and how to generate variable, continuous variable, binomial variable, power sum variable, and so on. Okay. So if you don't have, if you have any question, feel free to ask. Otherwise, feel free to leave and see you next time.